Hey guys, so this is our second part of the linear regression lesson, talking about how we interpret and deal with or find different pieces of information in a linear regression model. So if you remember from last time or from class time, that linear regression basically means we're trying to fit a linear model onto a specific set of sample data. So today, last time or in class, we talked about how to interpret slope and how to interpret y-intercept. We also talked a little bit about what a residual is, and we're going to continue talking about residuals in today's lesson, as well as a few other things. So today's objectives is that you will be able to identify and interpret parameters of a linear regression analysis, and to use given plots to determine the appropriateness of a linear model. So let's get started. Come on now. There we go. So the least squares regression line, first thing I want to look at is why is it called the least squares regression line? It's a very weird word that may be complicated to understand. So least squared regression line basically means, or it's the line of best fit. It's called that because it is the line that minimizes the sum of the squared residuals. So if you remember residual is that distance from each point to the line vertically. It's the distance between the predicted y value and the actual y value. So I'm going to go ahead and look at a silly little applet. The link for this applet is in the bottom of, like in the speaker notes section of this slideshow, if you look at it later, and you can kind of play with it. So let's say I have, here's a height versus shoe size data that was just on this website. That's very convenient since that's what we talked about in class. So basically, right, the squared residuals represent, let me move this up a little bit. So if I'm trying to guess the line of best fit, right, so maybe I'm trying to figure out what should the slope be and what should the y-intercept be to make this y-intercept or to make this line of best fit work. The regression line is going to be the one, so each of these, if you kind of look carefully, what it's doing is it's finding the distance and then it's squaring that distance. And when we add all those areas together, we want that sum, which is represented down here, to be as low as possible. So I'm trying to get that sum as low as possible, and I can kind of sit here and play with where does the slope and y-intercept need to be to make that sum as low as possible. So maybe I keep playing and try to get it as low as possible. That's pretty low. I'm going to come over here and show you what the actual line of best fit is. Ooh, so I wasn't quite there. It was a little bit off. But that is what that least squares refers to, is we're trying to make those squares, so the distance from the point to the line vertically, and then that distance squared, we want that sum of all those squares to be as small as possible. And that's what the line or that word refers to. So that's kind of a fun tool to play with to demonstrate that meaning. So let's go back to what we talked about at the end of last class, which is a residual. So the residual, again, is that difference between observed and predicted y value. Specifically, it's the observed y minus the predicted y. And we kind of talked about our line of best fit was actually going to miss most of the points. So those vertical distances between the point, each point in the line, are residuals. Okay? And if we plot each of those points as an ordered pair of x, comma, residual, we end up with what we call a residual plot, which will look something like this. So here's the original data. It's a bunch of different food items, their protein versus their fat. And down here is the residual plot. So the x is still protein grams, but now my y is the residual, so the differences between observed and predicted fat grams based on our linear regression model. So what that residual plot can do for us, if you kind of look at it, it's just taking that line of best fit and making it just a horizontal line at 0. And it helps to kind of magnify the differences that we're seeing between each point in the line and make them, they're kind of their own thing, the focus. When we look at a residual plot, what we're looking for is, does that residual plot have a pattern? A pattern in our case would be not a good thing, not a good kind of vote for linear. We'll talk about why. A pattern would indicate that our data may not actually truly be linear. It might look linear on the scatter plot, but it may not actually be linear when we deal with our residual plot. So let me show you an example to see what I mean. This particular residual plot, I would say, has no distinct pattern, which is what we want to see for a linear model, right? So if you're asked a question of, is a linear model appropriate? We want to check two things. We want to check the scatter plot. Does the scatter plot look linear? Because if the scatter plot looks like quadratic, then clearly a linear model is not appropriate. But we're also going to check this residual plot and look for a pattern, specifically usually a curved pattern. So let me explain a little bit. So here is a linear model up here, a scatter plot showing the height versus weight of American females aged 30 to 39, just a random scatter plot of old data from forever ago. Now, if I were to look at that, I would probably say our scatter plot looks pretty linear, right? It looks almost perfectly linear. I even have my line of best fit drawn on there, and it looks pretty good. But when I check my residual plot, I actually see that there is a little bit of a curve. So when I check my residual plot, I see that I have a curved pattern, which means that a linear model may not actually be the most appropriate model for this set of data. In fact, what's happening is that there's a very slight curve. You can kind of see it in our original scatter plot, but it's very, very hard to see. What this residual plot is doing is it's magnifying each of those differences and kind of blowing them up so that it's easier to see that there's a curve in the data and that we probably should be dealing with a different type of model rather than linear to explain the model or explain the differences in this graph. So that is where a residual model or residual graph can help us. You are never asked to create residual graphs, but you would be given them from time to time and asked to kind of refer to them in this situation. A couple extra practices just for funsies, and then we'll look back at our data for height versus shoe size. So again, the question that you might be asked related to a residual plot is a linear model appropriate for this data, or is it the most appropriate model for our data? So I'm going to give you a couple more examples. So let's assume we already checked each of these scatter plots, and the scatter plot looked fairly linear, so we know we're good there. Right? If this was my residual plot, a linear model would be good because I do not see a pattern in that residual plot, which is what I want. I want the points nicely scattered above and below with no obvious curved pattern. But what if that was my residual plot? That would be a big no, because I definitely see that kind of almost quadratic looking curve in that residual plot, which is not a good sign. That would tell us that our original scatter plot is probably a little curved and we just couldn't see it very well. So now let's look at our data. So this was the scatter plot, and this is the first period data. This is the scatter plot for our shoe size versus height data from our collection in class, right? I would say that scatter plot looks fairly linear, so we are good there. We do have, and I talked about this with my first period, which is what this data is from, but I do have potentially an outlier down here, but I don't think that's affecting that it's linear. I think we just kind of have a point that's not quite in the rest of the pattern. Here is my residual plot. So for this residual plot, I don't really see much of a pattern. Again, I do see we've got this kind of outlier, but again, it's not creating an overall curved pattern. It's just a point that's not necessarily fitting the pattern of the rest of the data. Okay, so for the most part, I do think we don't have a pattern. So what that would mean when I answer the question, is a linear model appropriate for our shoe size versus height data? I would say the scatter plot looks linear. The residual plot doesn't show any obvious curved pattern. So yes, a linear model is appropriate for this data. As in, I probably don't want to go to another type of model. I'm probably going to stick with linear. So that is how we talk about residual plots. So let's talk about a few other things that you're going to be asked. We've already dealt with our correlation coefficient, which is R. In general, correlation coefficient is a measure of the strength and direction. As we talked about last time, it's basically telling us how accurate our predictions are going to be from the linear model. This is actually our equation for R, for correlation coefficient. It's not super pretty. It's not something I would want to do by hand. Basically what we do is we find the z-score for each x coordinate, So for each x, I do that x value minus the mean of the x values divided by the standard deviation of the x values. Then I do the same thing for all the y coordinates. Each y minus the mean of the y's divided by the standard deviation of the y's. Right, so I've got all my z-scores for x and for y. Then for each individual point, I would multiply its z-score for x times its z-score for y, and I would do that for every point. I add together, this is the summation part right here, I would add together all of those products, and then I would divide by n minus 1, and that would give me r. It is not something that I ever want to do by hand because it would be ridiculous. So that is something that you are always given. We are given this formula on the formula chart for AP Stat, but it's not something you're ever going to use to do by hand. Typically, correlation is given to you as a data value in some form or another. That is the bell for the end of third period. So it looks fun, not really. We're going to use a calculator, or we'll just be given the R value. So interpreting the coefficient or the R, just as an example. So this was some data from our shoe size versus height example. Typically, now I did give you R in class for that, the correlation we talked about, but typically on this type of problem, you wouldn't actually be given R, you're usually given R squared. And we'll talk about what R squared means in a minute. So because we're given R squared, we do have to do a tiny bit of math to figure out what R is. R squared is exactly what it sounds like. It's R value, the correlation coefficient, squared. So if we know that R squared is 64% or 0.64, we do need to make sure and convert it back to a decimal for this. So R squared equals 0.64. What do we do to solve for R? We take a square root. So we take a square root from both sides and we get R equals the square root of 0.64, which is plus or minus 0.8. Again, if R was negative 0.8 and we square it, we would also get 0.64. So it could be either plus or minus 0.8. And if all we were given was the R squared and nothing else, I would have no idea whether it was positive or negative. But on this one, I do know it's positive 0.8 because I see that the slope of our line is positive. And our slope sign, positive or negative, should be matching the correlation direction. So we know this one's positive because our slope is positive. If our slope was negative, then we would know R would be negative. So it's got to match. Right? So interpreting that is what we kind of talked about last time. Right? The correlation coefficient, R, tells us that there is a moderately strong, so 0.8 is right there on the boundary between moderate and strong, so I can say moderately strong. Positive, again, because slope is positive, correlation between shoe size and height for students in this class. What you want to be careful of, if this was all we were given and there was no graph ever given to us, I shouldn't mention form being linear. It probably is, but if I don't have a graph to look at and see that it's linear, I can't say that it's fairly linear. If all I have is numbers to go on, right, I can't for sure say that it's fairly linear. I can calculate a correlation for any set of numerical data. Even if it's quadratic on the graph, I can still calculate an R for it. So it's really important that we only kind of talk about form if we have a graph to look at to describe the form. So let's talk about what that R squared value actually is. In statistics, we call this the coefficient of determination because we like to be fancy with our words. But the R squared value is basically another value that gives us an idea on how good the model is, the linear model is, at predicting our Y values from the X values. And we interpret R squared as a percentage, which is why it's typically given to us as a percentage. So the way we interpret R squared is something like this. We say about blank percent of the change in Y can be explained by our linear model for this set of data. Right? Whatever percent of the change or the deviation in Y can be explained by this linear model. So for our data, I'll come back to that in a minute. Our R squared was 64%. Again, it's usually given to us as a percentage because that's how we interpret it, is as a percentage. So what we would say for our data is that approximately 64% of the change in height, because that was our Y variable, 64% of the change in height for students in this class can be explained by our linear model for shoe size. So what that would mean is the other 36% of the change in height is explained by other models or other variables. So there might be other reasons your height is what it is besides just the size of your feet. So there are other components that go into that change that we see in height besides just your shoe size. If shoe size was the only thing that explained change in height, then our R should be 1, our R squared should be 1. 100% of that change in height is due to shoe size, right? But that's not really true. A lot of things go into how tall we are besides just our feet size, right? It's not that consistent. Okay, so going to go back to what I said here. Why do we have two measures of strength? Why would we not just stick with R correlation? Why are we doing R squared? Why do we got to make this complicated? What it comes down to, fourth period just started. So what it comes down to is R, or correlation, is really only a good measure when we're dealing with linear models. So R correlation is specifically for linear models. So in statistics, when we are dealing with nonlinear models, there is a way to calculate an R squared. It's not something we're going to get into. We don't do nonlinear regression in basic statistics. But there is a way to calculate an R squared for nonlinear models like quadratic models or exponential models. So what statisticians do, if they can't figure out for a set of data which type of model would be best, they run all of them and see which R squared is the highest. So that's where R squared is useful, is when it comes to comparing between different models to decide which model is the best one. So that's the gist of R squared and why we use it. All right, last thing, and then we're done with all of our interpreting. There's a lot of interpreting in this particular unit. The last thing we're going to have to interpret is something that's usually labeled as SE, which is the standard error of the residuals. Okay, sometimes it's reported as S or even just capital S. But what this number represents, it's basically like the standard deviation of the residuals. Okay, so residuals, the difference between observed and predicted Y values. Standard error is kind of like the average residual in a sense, or it's the average difference from the predicted to observed Y value. You kind of think of the line of best fit as kind of like our average, and then the distance from that is a residual, right? So that standard or average distance is what this SE represents. So what I might say for our data for this situation, if I were interpreting that value, is I would say that the typical or average difference between observed and predicted heights, because that's what our Y variable is, that difference between observed and predicted heights is a residual. So that average difference, or typical difference for students in this class is that SE value of about 3.025 inches. So on average, students are differing, their heights are differing from the predicted height by about 3-ish inches, right? This number is kind of telling us, again, how good is this model? If that SE number is really, really big for your set of data, that means our points are overall really far from the line, so this model is not very good, right? If that SE value is pretty small for our set of data, then that means overall the points are really close to the line, so this model's pretty good. Right, so it's just kind of another way of gauging how good is this model at making predictions and being accurate in those predictions. All right, that was a lot. Another thing that is linked in the kind of assignment for this notes video is what we call a regression cheat sheet. There's a lot of wordings and a lot of like little pieces that you have to know how to interpret really well. So that cheat sheet is just a good way for you to keep track of what are the different things that you need to memorize and know for your test. So that is all for this lesson video. See you guys next week.